Thank you everyone for coming out and your attention to this talk. I would like to start off by thanking my co-authors, Month Kola, Eric Phipps, and Umit Chalyark for all the hard work that went into developing this algorithm. I'd also like to thank funding sources, Sandia National Lab, the NNSA, and which funded this work as part of the Exascale Computing Project. And finally, I would like to thank the past Spurring Committee for providing me with the travel grant to actually be here in person to present this to you here today. So today I will be presenting on the FIST-HOSVD, the fused in place sequentially truncated higher order singular value decomposition. So kind of a mouthful, but let's get started. So start off be like low level and work our way up from there. So first off, what is a tensor? So a tensor is a multidimensional array. For example, a vector can be considered a first order tensor, a matrix could be considered a second order tensor, and this cube, which we see up here, could be considered a third order tensor. So one thing that's worth noting when you're working with tensorial data is that tensor storage requirements tend to grow exponentially with the size and number of dimensions, and this can quickly get out of hand in many scenarios. So the aim of the Tucker decomposition, also known as the higher order singular value decomposition, aims to compress a tensor by computing a smaller core tensor, which you see over here, and a series of factor matrices corresponding to each dimension. So in this case, an approximation at the original tensor can be recovered by multiplying this small core tensor along each dimension by this factor matrices to recover an approximation at the original data. And it's worth noting that this core tensor tends to take a much less storage space than this original representation. So how do we actually go about computing Tucker? Oh, sorry, scratch that. What are some quick applications of the Tucker decomposition? So the first, which I quickly mentioned, is data compression. So for example, the TuckerMPI project compressed over 6 terabytes of simulation data into just 167 megabytes with a 1E2 negative relative error. And up here is several diagrams from the paper, courtesy of Ballard, Kleinvex, and Kolda. And so here we have the original combustion simulation data set. And over here we have 2 different compressed versions at different levels of error tolerances. And as you can see, in both cases, the approximation appears to encapsulate a pretty high fidelity representation of the original data, which can be extremely useful for these large scale simulations. And in this case, using Tucker, you can reconstruct the entire or a single part of the data set if we want to work with a single part. And it's also worth noting that the error tolerance is related to truncation, which we will cover later in the talk. However, Tucker has several other applications in computer vision, signal processing, and many more. And generally, it's good at capturing latent multi relationships between variables. And much of this information we would lose if we just viewed it as a matrix, which what previous approaches did. So now let's quickly go over how we might go about computing Tucker. So the current state of the art algorithm is referred to as the sequentially truncated higher order singular value decomposition algorithm, and it's one in a long line of improvements over the original algorithm for computing Tucker. So let's quickly go over the ST-HOSVD algorithm, and we'll just quickly we'll discuss two main bottlenecks and go from there. So first, we'll initialize our core tensor G with the original tensor X, and then for each dimension, we'll first compute the gram matrix of the tensor. So the way we do this is we take the tensor, and basically what we're going to do is we're going to flatten it out into a series of row-wise contiguous submatrices, where each submatrix, which you see up here, has a number of rows equal to the size of the dimension along which we are taking the gram matrix, a number of columns equal to the product of the dimensions less than the current mode, and a number of submatrices equal to the product of the dimensions greater than the current mode. We'll then take this and multiply each submatrix by its transpose to yield a IN by IN symmetric matrix, and then we will take all i greater of these and reduce them together in order to form our in by in symmetric gram matrix. So once we have this gram matrix, what we're going to do is we're going to compute the eigenvectors and eigenvalues of the gram matrix, and then we are going to basically sum up the smallest eigenvalues until we hit our error tolerance, and then drop the corresponding eigenvectors and sort the remaining eigenvectors in this matrix U here. So once we have this, we are then going to take U transpose and multiply our current core tensor by it in a process known as tensor times matrix, or TTM for short. And so up here we have a quick example of the TTM just to provide some quick intuition for how it works. So here we have a 30 by 40 by 20 by 3 tensor, and we're going to multiply along the third dimension right here by a 15 by 20 matrix. So what we're going to do is we're going to take this tensor, we're going to flatten it out and matricize it along the third dimension, and then multiply it by our input matrix. And then once we're done, we're going to like review the tensor matrix as a tensor again, and we'll see that this dimension has contracted along the third mode to match the first dimension of the input matrix. And so the reason that we focus on these two kernels in the context of ST-HOSVD is that they form the two computational bottlenecks of the algorithm. So the gram requires IN, where IN is the current mode, times the product of all the dimensions in terms of flops, and then the TTM requires J times the product of all dimensions, where J is the number of rows in the input matrix, or 15 in our little example here. And in the context of this work, we're going to focus on the dense single node case. So let's quickly go over some quick limitations of the ST-HOSVD to see where we might try and make some improvements. So it's worth noting that in addition to the original tensor, we must allocate memory to store the intermediate TTM results, because each intermediate core of the tensor will be used at subsequent iterations of the algorithm. So for example, in this little example right here, we have our original tensor, we do our first TTM, this is the first core, and then the next iteration, we will use this core to compute the second partial core. And during the context of this, we have to maintain these two partial cores in memory. And in the worst case, when we get little to no truncation along the dimensions, as you see in this case, like we only went from 175 to 150, and here we only went from 120 to like 100, just as an example, we can consume up to 2x the tensor size of memory just to compute the decomposition. And so, as I'm sure many of you are aware, memory is a very limited resource, and we are often bottlenecked in this computation by the tensor exceeding the amount of available memory. So in this case, which can happen when the tensor is larger than a third of main memory or RAM, the ST-HOSVD is either unable to complete, or the computation might go out of core, in which case we might thrash between RAM and disk, potentially in some pretty catastrophic performance degradation. And so the goal of this work is we're going to try and alleviate this problem by computing the Tucker decomposition in place. So essentially what we're going to do, we're going to take the original tensor and we're going to overwrite the tensor with the core of the Tucker decomposition. And essentially in doing so, we will reduce the memory consumption. We compute the memory consumption by memory high water mark of the algorithm minus the size of the original tensor from the square of the largest dimension plus the product of all dimensions to just the square of the largest dimension. So we're no longer going to need to hold these intermediate representations. So as just a quick overview, just to reiterate, memory is a valuable language resource, and we're going to significantly decrease the memory consumption of computing dense Tucker from the square of the largest dimension plus the product of all dimensions to just the square of the largest dimension. Thus, if the tensor can be held in memory, then we can most likely compute Tucker, and we're going to do this while maintaining comparable and in some case decreased runtime. So we're going to do this through 3 novel optimizations. So the first is kernel fusion. We're going to show how we can combine the TTM and gram kernels together and improve the memory locality of the algorithm. We will then extend matrix tile and cache blocking techniques to this fused kernel operation, basically pose the computation as a series of cache blocks. And then finally, we're going to show how we can develop how we can prepare these cache blocks in place via a novel or an improvement upon existing cycle following based in place transpose algorithm. And essentially, once we prepare these cache blocks in place, we are then going to dispatch the cache blocks proportionate to the amount of available memory that we have access to, overwriting the tensor as we go. So let's start off with our kernel fusion optimization. Okay, so for those of you who aren't familiar with how tensors are generally stored, normally they're stored column major in memory. So if this is the first dimension, second dimension, third dimension, the first dimension here is contiguous memory, and then it goes as such memory. So this is the first, the 0th element memory, first, or 1, 2, 3, 4, 5, 6, and so on and so forth. So let's quickly look at if we're trying to compute the mode 2 TTM. So we can basically view this tensor as a series of contiguous submatrices. So here, our first submatrix is contiguous this way memory. You see 0, 1, 2, 3, 4, 5 here. And the number of rows equal to the size of the dimension that we're doing along, or dimension 2. Number of columns that we have is equal to the size of the product of all the dimensions less than the second mode, in this case, just 2. And then the number of submatrices that we have is equal to the product of dimensions greater than the second mode, in this case, 4. And so each of these we're going to take and multiply by our input matrix. This is a simplified example. Normally, this would be the remaining eigenvectors, transpose eigenvectors that we computed in the previous step. But for here, we just have 1s and 2s just to make it easier to compute in your head. And then, so we're going to multiply each of these by this input matrix. And this right here is the tensor after the TTM along the second mode. So after this, we're quickly going to look at the gram matrix along the third mode of the result from this TTM matrix. And the first thing we're going to note is that the first row of the matrixized tensor is just one of these entire submatrices, but just in a row vector. And this is true for all of the rows in the mode 3 matrixization of the tensor. So then we take this and multiply by transpose, and this is the gram matrix of the mode 3 matrixization of this tensor. Now, the fact that this row is just one of these submatrices is important because we can see from here we can see how after computing one of these submatrices in the mode 2 TTM, we can immediately, while everything is still in cache, compute the first entry in the gram matrix. And basically, we can do this for every entry in the gram matrix, and the goal here is to keep everything in cache. And in the literature, it has been shown that these kernel fusion techniques have been able to greatly improve memory locality, and this is especially effective in the GPU case, which you leave for future work. So from here, let's quickly move on to the next optimization technique. So the next one is we refer to as tensor tiling. Basically, we're going to take our matrixized tensor and pack into a series of cache blocks that are cache friendly and go from there. So here in our matrixization, the current dimension IN is contiguous in memory. We are going to select columns that are IN less offset in memory, pack them together into a IN by IN plus 1, where IN plus 1 is the size of the next dimension that we're going to be working with, and pack into a cache block. We'll then do a partial TTM result and write it out, write the result row major in memory into this JN, where JN is the size of the number of rows in the input matrix, by IN plus 1 intermediate result. And then from here, we're going to do a logical transpose into a IN plus 1 by JN column major matrix. and then immediately take this and compute, multiply by its transpose to form a partial gram result for the next dimension. It's worth noting here that this transpose doesn't actually require any data movement. We just change how we logically view the partial result. However, it does require discontinuous memory access in order to pack the blocks into them in the first place. And so after doing this for all of our cache blocks, we'll eventually end up with the entire TTM result and the entire gram result, which we have been accumulating into over the course of all these cache block operations. And so it's worth noting that the tensor layout essentially evolves in memory over the course of computation to prepare the tensor for the subsequent iterations of the algorithm by having the next dimension that we're working with be contiguous in memory. So once we have this in place, we can basically reformulate the ST-HOSVD into the fused and sequentially truncated higher order singular value decomposition, or FIST-HOSVD for short. I was very happy with how that acronym turned out. But so it's basically very similar to the ST-HOSVD, except for we start off with the first gram computation as normal, and then the intermediate gram and TTM computations, we use this fused representation, and then finally we'll end with a normal TTM along the last dimension, and that concludes the FIST-HOSVD algorithm. The only one thing that's worth noting is that in this case, the core tensor will have its core entries like permuted in memory, and in order to recover the approximation, you'll basically have to do this process in reverse. There's a slight caveat there, but you will still arrive at the correct decomposition in the end. So that is the second opposition that we applied. And then finally, we're going to show how we can prepare these cache blocks in place in order to do this computation, make this computation more memory efficient. So in order to do this, we start by noting that for the nth iteration of the algorithm, the matrixized tensor can actually be viewed as having in by in less, where in less is the product of all dimensions less than the current dimension, entries in one column, and then we'll take each of these columns and stack in plus 1 together to form this logical submatrix. And from here, right now, at this moment, the entries are contiguous this way, column major in memory. But if we just make it row major in memory, we'll have prepared our cache blocks for this logical submatrix. And from here, we see that it's actually just a matrix transpose. And from here, we can leverage a bunch of existing in-place transpose algorithms to do this transpose in place. So there are several existing in-place transpose algorithms in the literature. But in the context of this work, we chose to improve upon just the traditional in-place transpose algorithm based upon cycle following. A quick intuition on how the in-place transpose algorithm based upon cycle following works is, so here we have a little like toy example that's column major in memory, and we're going to transpose in place by taking each element except for the first and last elements, taking its linear index in the matrix, multiplying it by the number of columns, and then taking the modulo of the number of elements in the matrix minus 1 to get the next entry in a cycle. And basically, if you continue to apply this, you'll end up with a cycle through the matrix, which you can see in the small example. And once you have, and each cycle is every entry in the matrix besides the first and last elements are a member of one of these cycles, and each cycle is they do not overlap. They're and so from here, you basically take each element and you shift it once in the cycle in order to get a in-place transpose. And at this point, each step, you basically only have to store a single element in order to like get into the transpose representation. Traditionally, this theoretically, it requires less element access than other in-place transpose algorithms. However, in practice, it traditionally suffers from poor memory locality due to the almost pseudo random element access in the matrix. However, we improve the memory locality of this algorithm by accessing them. Instead of accessing single elements, we access a series of contiguous elements in order to improve the memory locality of the algorithm. So here we'll view one of these, the IN elements, as a single element of the matrix, and then we'll group several of these together in order to improve the memory locality. And we plan to explore this in this improved in-place transpose algorithm in the future work, which we refer to this as the interleaved in-place transpose algorithm, or IIPT for short. So bring all of these operations together, we will show how we can quickly compute Tucker in place. So first, we are going to do an interleaved in-place transpose to prepare the cache blocks. And from here to here. From there, we will de-interleave the cache blocks into the amount of auxiliary memory that we have in this step. And then we will dispatch all of the cache blocks that we stored in our auxiliary memory, computing the partial TTM results, overwriting the original tensor, and then accumulating into our gram matrix. So the resulting algorithm looks very similar to the FIST-HOSVD, except for instead of our fused kernel, we have our fused in-place kernel. And once again, the advantage of this is that we can avoid allocating memory to hold the intermediate TTM results. And thus, if we have at least the square of the largest dimension in memory, then we can compute Tucker. So let's quickly go over some experimental results. So we ran on several nodes at San Diego National Labs, each with 28 cores and 256 gigabytes of memory. This memory allocation is extremely important because if we exceed this, then the computation will either terminate or cause the node to crash, much to the consternation of the server admins. And so we run on 3 different data sets. The first is a randomly generated high rank tensor, where each slice is 64 to the 5th. The second is a homogeneous charge compression data set, which forms a 4th order tensor from a simulation of turbulent auto-ignition over a 2D spatial domain, where each time slice is 672 by 672 by 33. The entire data set here is, I think, around 76 gigabytes of memory. And finally, we have a statistically planar 5th order tensor from a simulation over a 3D spatial domain, whose 4th mode is 11 solution variables at each grid point, where each time slice is 500 by 500 by 500 by 11. Each time slice here is around 11 gigabytes, just for context. It's also worth noting that this is a relatively low rank tensor, which we will, this helps to explain the results in the subsequent slides. So here are some quick scalable studies over varying the number of threads. We see that generally the fused implementations tended to perform on layered dimensions due to the cache blocking, whereas the traditional ST-HOSVD algorithm tended to struggle with the long, skinny major locations that most BOS implementations aren't optimized for, which helps to explain why the FIST-HOSVD is around 2x faster than the next best alternative here. As also, just for context, we were comparing to TuckerMPI, which is the existing state-of-the-art ST-HOSVD implementation. And it's worth noting that the cache blocking doesn't indeed incur some data movement overhead, but we generally make this up with the increased memory locality of the computation. And we plan to add in support for processing conventions out of order in future work. And the general takeaway from the slide is that we can maintain comparable runtime. And finally, here's the slide that we are really where we see the real improvements of the FIST-HOSVD. So here we see the FIST-HOSVD consumes significantly less memory than other algorithms, which makes sense because our asymptotic bound has gone from I squared max to the product of all dimensions to just the square of the largest dimension. And we compute the memory consumption as the memory hierarchy of the program minus the size of the original tensor. And so, for example, here the traditional ST-HOSVD algorithm consumes around 161.9 gigabytes of memory, whereas the FIST-HOSVD consumes around 1.2. Also worth noting, we allocated a 1 gigabyte array of auxiliary memory for the FIST-HOSVD, and the additional memory usage comes from the gram reductions, because each thread needs to allocate a gram matrix and reduce it together. So that's where the extra 0.2 comes from. And all bars not shown did not complete due to running out of memory in these cases. In these cases, the FIST-HOSVD was the only one that was able to complete. So yeah, so just a quick summary. We have reduced the memory consumption of commuting dense Tucker from the square of the large dimension plus the product of all dimensions to just the square of the large dimension. Thus, we've significantly decreased the memory consumption of FIST-HOSVD for dense Tucker. Thus, if the tensor fits in memory, then the FIST-HOSVD can mostly likely compute Tucker. And we've done all this while maintaining comparable and sometimes decreased runtime. For future work, we hope to add and support processing dimensions in any order, as the kernel fusion provides similarly the base performance results along the later dimensions. We hope to compare the IIP algorithm, the interleaved in place transpose algorithm, to other existing in place transpose algorithms, and we hope to eventually complete a GPU port. As everything is currently implemented in Cocos, however, we just have not finished our GPU implementation. And actually, the kernel fusion optimization was actually originally intended for the GPU case, based on the past literature. And we actually expect to see even bigger improvements in the problem size that we can compute, because the device memory tends to be even more limited than the host memory. Thanks. I apologize for going a little bit over time, but yeah.
Thank you for the presentation. Is there any question from the audience or online? Yes, please.
Hi, that was a great talk. So I just had a quick question. It seems like you put a lot of effort into maintaining memory locality and contiguous access. Are there any sort of design challenges for the GPU port, or is it just a matter of implementation time?
Yeah, so in the case of the GPU port, I would foresee the input. So right now, the in-place transpose algorithm, the number of element accesses and actual operations it requires is entire factor of n less than the number of operations required for the multiplication. So right now it doesn't have it's caused significant overhead. However, in the case of the GPU port, the major multiplications will be significantly faster. In which case the in-place transpose might become more of a problem. And so thus we've worked out two potential solutions to this. One consists of doing the in-place transpose on the host while processing the cache blocks on the GPU, thereby overlapping the computation time for the two. And the second solution is just to basically pull the columns into the cache blocks from the host to the device, and then write out the solution into a separate area of memory on the host. This would probably decrease this problem size that we could compute with the FIST-HOSVD by around 2x, but it would be asymptotic with the size of the host memory as opposed to the device memory. In many cases, the host memory tends to be significantly larger than device memory, so we would still see pretty significant savings in this case. And actually, I think that is probably what the solution that we'll go with, because it'd be significantly easier to implement and we would expect to be rather fast. So, thank you.
Any other question from the audience? From the results I saw, I suppose is a single node implementation you're solving.
Exactly. So right now, the program framework which we implement this in Gen 10 is primarily designed for the single node case. However, it is worth noting that TuckerMPI does support distributed multi-node implementations.
Is there any plan for your solver to also be ported for distributed?
That's a really good question. So we would probably focus on doing the GPU port before we focused on the distributed case. However, I think porting this to the distributed case should be feasible, as the each cycle in the in-place transpose algorithm would lead to a point-to-point communication, similar to what's used in like Scalapack, and we think we could get pretty decent performance. The communication overhead might be, it would be a consideration, but I think we could still do it. That's a bit far in the future, though.
Okay, thank you. Any other question? If not, we thanks again the speaker. And
thank you.
Thank you for joining this session. And now it's coffee break.